These are the 6 problems proposed for lesson 36. It's about differential equations, and we'll solve it. Okay, let's go to solve the first problem. It's the rate of change of y. The rate of change of y respect to the time. So it's the rate of change respect to the time is proportional k by y. Or maybe the equation that you are solving is the derivative of y respect to the x equal k by y. Immediately that we see this equation, we know the solution. We have worked the solution in the previous example, and the solution to this differential equation is c e to the kx. Perfect. When x equals 0, y equals 6. So 6 will be c e to the k 0, or 6 will be c a to the k by 0 is a to the 0, or 6 will be c by 1. So c will be 6. C will be 6. So the equation is 6 e to the kx, but still we don't know the k. But it says, the second information say, when x equals 4, y equals 15. So 15 equals 6 e to the k4. And this allows me to find the k. How I will find the k? 15 divided by 6 is e to the k4. 15 divided by 6, if I take the natural log, it will be the natural log of 15 divided by 6 equal 4k by the natural log of, well, I'm going faster, is equal to the natural log of e to the k by 4. By the natural log of k divided k e to the k4 is k4, is 4k. So 4k is the natural log of 15 divided by 6. So as a result, so this allows me to find the k. So the k is 1/4 natural log of 15 divided by 6. If you go to your calculator, you will find that k is, so the k, if you use your calculator, will be 0.2291. So the solution will be y of x equals c e to the kx, or y of x equals 6 e to the 0.2291x. So now the problem is asking, solve the differential that model verbal statement. The rate of change is proportional to y, so you remember that the rate of change for this y, the rate of change is proportional to y, to this height. But the problem is asking, then find the value of y when x equals 8. Well, I have the equation. So y of 8 is equal 6 e to the 0.2291 multiplied by 8. You go to your calculator and you will find y of 8 and approximate something. But this is not the correct way to do it. The correct way to do it is to introduce the k. So y of x is c by e to the kx. Y of c is 6 and k is 1/4 natural log of 15 divided by 6 by x. Now, when x equals 8, y of 8 will be 6 e to the 1/4 natural log of 15 divided by 6 multiplied by 8. So y of 8 is 6 e to the 8 divided by 4 is 2. Is 2 times natural log of 15 divided by 6. So it will be y of 8 will be 6 e to the natural log of 15 divided by 6 square. So y of 8 is 6, but e to the natural log of 15 divided by 6 square is 15 divided by 6 square. And this is y of 8. You don't need any calculator to do it. Well, maybe now you need the calculators, but indeed you don't need the calculators. It's 6 by 15 squared is 225 divided by 36. 6 divided by 36 is 1/6, so it's 225 divided by 6. And 225 divided by 6 is whatever it is. I think it's how much? 70 maybe? 30, 30, 37, 37.5. And this is the result for y of 8. Okay, let's go to solve this problem. It's very similar to the previous one. It says the rate of change of n. The variable is not y, it's n. Is proportional to n. So it's the rate of change, maybe respect to time, because they mentioned the time, is proportional to n. So this is the equation that it says. It says that when t equals 0, n 0, the initial value, or n of 0 equal 250. It says that when t equal 1 second, or 1 hour, or maybe 1 year, or maybe 1 million of years, the amount, the n, is 400. So 400 is n of 1. Write and solve the differential equation. Okay, we already solved the differential equation. We already write the differential equation, and we need to solve. And the solution is n of t equal e c n 0, the initial amount, by e to the kt. This is the solution. Why? Because if you start with this equation, k by n, and you do separation of variables, you will find this equation, k by d dt. If you integrate both sides of the equation between n0 and the final n, and between 0, t equals 0, t equals 0, and the final time t, the integral of the left side will produce natural log of n evaluate between n0 and n. So it will produce natural log of n divided by n0. So this is natural log of n minus natural log of n0, which is natural log of n divided by 0, and in the right side of this equation is k by t minus t0, but t0 is 0, so it's k by t. So it's easy to find now that if you do e to the kt and e to the natural log of x of n divided by n0, e to the natural log of n divided by n0 is n divided by n0 equal n to the kt, so n of t is equal n0 a to the kt. So we have solved the differential equation, and now we have to write the equation. N0 is the initial amount of substance, that is 250. 250 e to the kt, but we don't know the k, but we know some information. We know that in t equal 1, n equal 400. So n of 1 is 400. So 250 by a to the k by 1 is 400. So the equation that I would have is 400 equal 250 e to the k. And this allows me to find the k, because 400 divided by 200 will be the k. If I take natural log on both sides of the equation, I will find that the k is 400 divided by 250, the natural log of this. This is the k. So what is the solution? The solution is n equal n0 e to the kt, or n0 is 250 e to the natural log of 400 divided by 250 t. This is the solution, n of t. N of t, 250 e to the natural log 400 divided by 250 by t. And pay attention that the k is something positive, because it is the natural log of a number that is bigger than 1. So the n of t, it starts at 250 and grows exponentially. It doesn't grow, and the slope here is not 0. So let's go to represent here. It starts at 250, and the slope does like this. Okay, now it has a slope at the point 250. At the point x equals 0, y equal 250 need to have a slope. Okay, this is the solution. Let's go to the problem number 3. It's a radioactivity of radium. Radium is like uranium, it's unstable atoms with the nucleus expelling particles, and have a half-life approximately of 1,599 years. What percent of the given amount will exist after 100 years? So the equation says that the amount n, let's say n, the amount of radioactivity substance follows this equation. The change in the radioactivity substance respect to time is proportional to k by n. And what we have found that n of t follows the solution of this equation. And the solution of this equation is c by a to the kt. In this case, the k is negative because the amount of substance star and n0 is going to decrease. And after 1,599 years, the amount of substance is exactly half n0 divided by 2. This is what it means, has a half-life. So after one, and the problem is asking you, when you are here at 100 years, what is the amount of substance that remains? So all the information is here. So let's go to use these solutions to find the solution to the problem. So initially there is an amount at n0. So let's go to put the n0 here. N0 instead of c, n0. Okay, the n0 is the c, the initial amount. What it say that after t, when t equal 1,599, the amount of substance is half. So n of 1,599 is n0 divided by 2. So the equation, this equation will read that this is equal to n0 e to the kt, but t is 1,599. So this will allow me to find the k. So what what will be the k? So the equation will say 1/2 equal e to k 1,599. So if I take the natural log in both sides, the natural log of 1/2, which is something negative, natural log of 1/2 is negative, is the natural log of the right side of this equation. And the natural log of the right side of this equation is k by 1,599. So the k is 1/2 natural. The k is 1 divided 1,599 by the natural log of 1/2. And this k is negative because this natural log of 1/2 is negative. So a number that is negative multiplied by this 1 divided by 1,500, it will be a negative number. So what will be the solution? The solution will be n equal n0 a to the kt. But k is, well, let's go to right here, kt. So it will be n0 a to the k. We already know what is the natural log of 1/2 by t. Now let's go to answer the question, what will happen to the amount of substance after 100 years? After 100 years, the amount of substance will be the initial amount multiplied by e to the 1,599 natural log of 1/2 multiplied by t multiplied by 100. So this will be n0 e to the 100 divided by 1,599 natural log of 1/2. And this will be n0 e to the natural log of 1/2, raise the number 1/2 to 100 divided by 1,099. And e to the natural log of the number 1/2 is the number. E to the natural log of 1/2 is the number 1/2 raised to 100 divided by 1,599. And now, what is the percentage? The percentage is n divided by n0. And n divided by 0 is 1/2, 100 divided by 1,599, or approximately 1/2. 100 divided by 1,599 is 0.063953909, whatever. This is approximately, let's go to do it, using the calculator, of course. You will find 0.9575. So 0.9, it means that 5% has disappeared. And the remaining is, after 100 years, the percentage of the amount of substance that remains is 0.95. 95% of the substance will stay there after 100 years. But after 1,599 years, only half of the substance will remain. So the problem say like this: you initially have bacteria. You don't know how many bacteria you have. So the number of bacteria in a culture is following the law of exponential growth. The law of exponential growth, it says that the number of bacteria is the initial amount of bacteria multiplied by e to the kt. So it says there are 125 bacteria after 2 hours. So you measure the number of bacteria after 4 hours, and you realize that it's 350. So it says what is the initial population of bacteria, and also say how many bacteria there are after 8 hours. So the models say that the bacteria are growing according to the exponential law. Okay, so let's go to find the K and to find the initial amount. So we know that when T equal to N is 125. So the equation that we will have is that 125 will be N0 A to the K multiplied by 2 hours. So the K is something per hour. K by T have no units. So e to the kt, K have the unit of second minus 1 or hours minus 1. In this case, we'll have the unit of hour minus 1. So this is the first equation that I will have. The other equation that I will have is that when t equals 4, the n is 350. So this will allow me to write this equation. N 350 and 0 e to the k by 4. And the k is per hour. It's a number per hour, have units per hour. So if I divide one equation between the other equation, let's say that I divide equation 2 between the 1. So the solution, if I divide, it will be 350 divided by 125. The N0 will cancel. E to the 4k divided by e to the 2k. So 350 divided by 125, if you reduce, will be 14 divided by 5. And if you reduce e to the 4k divided by e to the 2k, the division will produce e to the 2k. And now what I want to find is the k. I will take natural log in both sides of the equation. So the natural log of 14 divided by 5 will be equal to the natural log of e to the 2k, because remembering that natural log and exponential function are inverse function, the natural log of e to the 2k is 2k. So 2k is natural log of 14 divided by 5. As a result, I found the k. The k is 1/2 natural log 14 divided by 5. And you don't need to use your calculator. There are, if you realize all the problems, if you need to use the calculator, you have to use it at the end of the problem, not in the middle of the problem. It's a big mistake to use the calculator in the middle of the problem. So this is the k. And the problem is asking me what is N0. What is the initial amount of bacteria that exists at n equals 0? So I can go to equation 1, this one, to this equation, and I can plug in the k here. I can find the N0. Let's go to do it. On equation 1, I will say 125 equal N0 unknown, e to the k. K is 1/2 natural log of 14 divided by 5 multiplied by 2. Now the 2 will cancel. These 2 will cancel. So it will be 125 will be equal N0 e to the natural log of 14 divided by 5. 14 divided by 5. And what is e to the natural log of 14 divided by 5? Is 14 divided by 5, 125. So n0 will be 5 times 125 divided by 14. Or the amount will be 5 by 100 is 500. So it's 600, 625 divided by 14. So this is the amount. Now you can use your calculator to find n0, but you don't need, it's a mistake to use the calculator in the middle of the problem. Now question 2 say, find the initial population, we already found. Also, how many bacteria would be after 8 hours. So it's an exponential growth. It's something that is amazing. It will surprise you, the exponential growth. So n of t is n0 e to the kt. We have to remember that the k is positive. K is positive because it's a growth where the number of bacteria is bigger and bigger and bigger. If the K were negative, the number of bacteria would be smaller, smaller, smaller. Okay, so the n of t will be the n0, 625 divided by 40, multiplied by a. The k is here is 1/2 natural log of 14 divided by 5 by t. This is my law. This is the law how the number of bacteria is growing up. Now the problem is asking me how many bacteria will exist at time t equal 8 hours. So easy. N of A will be 625 divided by 14 e to the 1/2 natural log of 40 divided by 5 multiplied by 8. As a result, the number of bacteria will grow up. What it means that the growing up is exponentially is you start at certain amount n0. In this case, I think 80 is 625 divided by 14. In the first seconds or per hour, the amount grows up. And it's grow up a certain amount. What is the growing up? The growing up is here. This amount is the growing up. But after the following second, the amount that will grow up will be bigger, much more bigger than the previous amount. Why? Because the amount that it will grow up depends on the existing amount. The amount that exists here is this amount. The amount that exists here is this amount, n0. So the curve will follow an exponential curve. After another second, let's say 3 hours, the growth will be even bigger. So you realize, let me put it, they will grow in red, they grow, the change in the function, the change in n. So the change in n depends on the amount of substance that exists previously. So the change in, well, previously no, it exists at this moment. So the change in n will grow up. So this is why they were very scared with coronavirus, because you know that was an exponential growth, the laws that govern the way that the virus is growing up, so it can infect the whole world. Let's go to the next problem. Minus, well, of course you can find a value for n of a. Let's go to find the value for n of a. N of a will be 625 divided by 14 e to the 1/2 natural log of 14 divided by 5, I think is the K, is 14, not 15. Is I remember it was 14 divided by 5. Let's go to check it. 14 divided by 5 multiplied by 8. So 8 divided by 2 is 4. This 4 will go up to the 14 divided by 5. So n of a can be written like this. You see that we are not using any calculator. N of a is 625 divided by 14 e to the natural log of the number. A divided by 2 is 4, so it's 14 divided by 5 square. So e to the natural log of 14 divided by 5 is 14 divided by 5 square. So it will be 625 divided by 14 multiplied by 14 divided by 5 square. And now this 14 square, 625 multiplied by 14 divided by 5, because 114 will go with this 14. And now is the moment to use the calculator. So 125 divided by 5 is 100. Well, you don't need to use the calculator, it's 100. 125 multiplied by 5 is 625. Multiply, so this divided by this is 125 multiplied by 14. And now you may find you can use the calculator. 125 by 14, whatever it is, this is the number n at the time 8, and you see how they have grown up, the number of bacteria. So I don't remember what is here. After 8 hours, the population of bacteria will grow up. Incredible. Okay, let's go to the next problem. So let's go to do problem 6. It's when an object is removed from a furnace and placed in an environment with a constant temperature of 80 degrees Fahrenheit. So 80 degrees Fahrenheit is the environment, is the temperature of the environment, and the object have a temperature of 1,500 degrees Fahrenheit. It's better to work with degree Kelvins in physics, but it doesn't matter, it will work. So what will happen is that the environment, 80 degrees Fahrenheit, 80 degrees Fahrenheit, is a big environment, very, very big. It's like the sea. So the object will release heat to the environment. The environment, because it's very, very big, the environment will not change its temperature, will have 80 degrees Fahrenheit. But the object will cool, and what it says is that after this is t equals 0, is core 80 degrees, its core temperature 1 hour at t equal 1. After heat removed, the temperature of the object is 120. So find his core temperature after the object is removed from the furnace. So the temperature is decreasing. So there is a K here that is negative. We need to specify the load that is governed the temperature. The change in the temperature per unit of time, the derivative of the temperature with respect to the time, is K by the temperature of the environment, T0, minus T. Let me think if this is correct. If I say that this is the law, I might say that t is bigger, so I will put the k positive. I will impose the k positive k. Now I would say, well, if T0 is 80 degrees and T, the temperature, this T, is the temperature of the object, the same T that is here, this will be negative. So the slope, the change in the temperature, the function will be decreasing. So this should be the equation for an object that is decreasing its temperature. But the equation, because I want a k that should be negative, the equation should be this one. ddt, the change in the temperature respect to time, should be k t minus t0. And now the k should be negative. So this is the equation. Let's go to write the equation. Is the change in the temperature respect to the time equal k by t minus 80. T0 is the temperature of the environment. T is the temperature of the object. And the object is changing its temperature because k is negative, and because k is negative, T initial is 1500, this is positive. But the k is negative, this is negative. So the slope will be negative. And now I have to solve this equation. How do we solve this equation? You know. How? You know. How? Separation of variable. ddt divided by t minus 80 will be k by ddt. This is time. This is temperature of the object. This is the temperature of the environment. And what I want to find is what is the temperature of the object as a function of time. We know that the initial temperature is 1500. And what we expect with this law is that the temperature will go downward, down, down, down. And eventually he will arrive the 80 degree when the time is very, very long. So how we solve this equation? We integrate. We integrate both sides from the initial temperature, 1500, to the final temperature that we will name as T. T is the final temperature of ddt divided by t minus 80 equal the integral from the initial time, it is 0, to the final time we call t final, t, of k by ddt. So in the left side of the equation I will have k by t minus k by 0. And on the right side of the equation I will have natural log of t minus 80 evaluated between 1500, when t is 1500, when it's t. So it will be the natural log of t minus 80 minus the natural log of 1500 minus 80, or equal k by t, t time. So the natural log of t minus 80 minus the natural log of t minus 80 is the natural log of this. And now it will be written like natural log of t minus 80 divided by 1420 equal k by t. And now e to the natural log t minus 80 divided by 1420 e to the kt. E to the kt. So t minus 80 1420 e to the kt. So T, the temperature as a function of time, will be 80 plus 1420 e to the kt, and this is the solution. So we can check. If t equals 0, t of 0 is equal 80 plus 1420 by e to the 0, which is 1500. When t goes to infinity, t at the infinity will be 80 plus, I need the k to be negative, because I need a to the kt to decrease to 0 plus 0. 80. Now let's go to find the k. The information of the k should be in the problem. Where is the k? The information is here on this 1120 degree after 5 hours. This is the k. Here is the information 1120 at t equals 5. So let's go to find the k. So we already solved the equation. We know the temperature is this equation, and we know we have to find the t. So we know that. Now we know that when t equals 1 hour, the temperature at 1 hour is 1120 degrees Fahrenheit. So we plug in this information in our solution. The solution is here. So it says that after t of 1 is 1120 equal 80 plus 1420 e to the kt, e to the kt, e to the k by 1. And this equation allows us to find the k. How we will find the k? Well, easy. 1120 minus 80 divided by 1420 will be e to the k. So 100,000, this will be 1040 divided by 1420 e to the k. So taking natural log in both sides, the natural log of 1040 divided by 1420 is the k. So now I can go back to my equation. N of t equal n0 equal 80. So no n of t of the temperature as a function of time. T of t is 80 plus 1420 e to the kt, e to the natural log of 1040 divided by 1420 t. And what it says, this equation? It says that the temperature T, it goes like this. When the time is 0 hours, the temperature of the object, it was 1500. I can see here that is true. When t equals 0, e to the 0 is 1, and this is 1500. As the times goes, the temperature decreases and decreases in an exponential way. When the time is 1 hour, the value of the temperature is 1120 degrees Fahrenheit. then I can find the temperature at any time. Let me read the problem to say if it's to see if it's asking anything else. Find the core temperature 5 hours after. Okay, so T of 5. So you have this equation now, and let's go to find T of 5. T of 5 will be 80 plus 1420 e to the natural log of 1040 divided by 120 multiplied by 5. So this is equal 80 plus 1420 e to the natural log of 1040 divided by 1425. This is the number. So it will be T of 5 hours. The temperature after 5 hours will be 80 plus 1420. So e to the natural log of the number is the number. Multiply by 1040 divided by 1420 to the 5. And now you can use your calculator to obtain the final number of the temperature at 5 hours as 379.20 degrees Fahrenheit. So the temperature decreased from the initial temperature at time 0, T of 0, of 1500 to the temperature 337 after 5 hours. So it starts at 1500, it goes downward in an exponential way, and what is 5, the temperature becomes 379 degrees. This is the idea. Okay.